So today we have Jakub Steiner, and he will talk about a paper entitled Growth and Likelihood. Jakub, the floor is all yours.
Thanks for having me. This is a paper in progress. It's not actually written, so all the comments and feedback is particularly useful. We study stochastic growth, which we understand in quite an abstract way. For us, it's just a multiplication of random variables. And in this abstract way, this allows to connect seemingly distinct topics. So a stochastic growth within economics would mean for us growth of wealth, and wealth is just a product of random returns. But seemingly far away in statistics, you could be interested in a likelihood of a sample or a growth of it as you collect more data, but likelihood of a sample is again just a product of likelihood of random data points, again of random variables. And in both these cases, you are interested in strategies, in be it an economic strategy or a hypothesis in the context of statistics that maximize this growth rate. And so given the underlying similarities in the mathematical structure, it is natural that some insights across those two disciplines will have a same structure. And this is the point of our paper, that we will discover some connections between an economic growth and some features from statistics. On general level, the insights that we try to convey can be formulated as this claim that optimal policy, the one that maximizes the growth rate, seeks consistency with the outcomes it generates. Now, on that level, abstraction is probably difficult to comprehend. So let me tell you how it exhibits within economics and then within statistics. So within economics, and this will be our main economic insight, we find something which we call a meritocratic principle, which says that good strategies, those that maximize growth rate of wealth, also maximize consistency between some wealth allocation and some measure of contributions to the wealth, which we call merit. So somehow merit and allocation of wealth should be as consistent as possible for the growth rate to be high. Now, there is an area from statistics or on the boundary of statistics, cognitive sciences, and machine learning called predictive coding, which is about how brain works or how those artificial machines work. And in that literature, it is known that a good setup of a brain or a machine maximizes consistency between a prediction of a system about the sensory information and the actual received sensory information. And it turns out that mathematically, that is equivalent to that meritocratic principle that I was trying to convey here, and I will be formulating it more clearly once the math will be developed. So this is going to be about economic growth. It's going to be, or the economic part of it is going to be about economic growth. We are going to ask how redistribution of wealth can affect growth rates. And there is a bit of a kind of empirical puzzle, because it's known now that redistribution can enhance growth. It sometimes harms, sometimes helps, but the positive part is perhaps more puzzling. And there is a neoclassical solution to the puzzle due to Stiglitz, who says, well, the returns are decreasing. And so if you take money from the rich people who have low marginal returns and give it to poor people who have high marginal returns, well, that's going to help. And I just want to emphasize that our explanation for the impact of redistribution growth will be different. Our returns will be constant returns, but they will be uncertain, and redistribution in our model will act as a hedge, as a way to substitute active learning. We will be heavily relying on information theory. So there is a long tradition within information theory that studies growth of individual wealth of a financial investor who is hedging optimally his portfolio. And that literature, by the way, connects well to Arthur Robson's series of papers, which has a biological counterpart. We will touch upon some results from machine learning and from predictive coding literature. In particular, we'll touch on what is called a variational method to Bayesian updating. So it turns out that machine learning literature or cognitive sciences literature admits, unlike economists, that Bayesian updating is hard. And it can, by Bayesian updating can be formulated as an optimization problem. We do that as well. And we provide some alternative proofs relative to the proofs that exist in those literatures. And those proofs that we provide are based on intuitions that come from economic growth. So with that, this is the end of the introduction. Now the actual talk comes. It will have 3 parts. There will be like the most economic part, when I will set up and what we think is an economic model. It's almost a macroeconomic model, but very stripped down. We will formulate the main results, and then we will be I will move to the section called proof. There will be more information theory than economics in that part. And then once we will have that, then I will move to the last section if the time will work out. And I will reveal that everything that we have done has been understood in a very different context of predictive coding. All right. So before I will give you the model, let me spend one slide on the notation because it's a bit unusual and has proved to be confusing in other talks. So if I wanted to talk about probability distributions, I would probably denote it by P, and X would be an argument over which the probability distribution is. And if there would be some covariate Y, then I could talk about the likelihood functions, just conditional distributions of Y given X. And then if I would specify both the probability distribution Px and those conditional probability distributions, then I would have a whole system of functions, which I would call a joint probability distribution, or I could marginalize it and I would have a marginal probability distribution of Y, or I could turn the conditioning upside down and I would have a conditional distribution of X over Y. And I would probably it would not be offended if I would call all of these different functions by the same letter P, and I would distinguish between them just by specifying the arguments. So here is what I'm going to do. For our purposes, it will be useful to extend this notation outside of the probability distribution. So I will still have a probability distribution Q of X, but then I will have some generalized likelihoods, which will be just positive functions of 2 arguments of Y and X. They will not be conditional distributions because if you sum them over Y, they would not add up to 1. But yet I will go on and I will write functions that will, by notation, appear to be either a joint probability distribution, marginal probability distribution, or conditional probability distributions. I will just keep the formulas that we are used to for the true probability distribution, and I will talk about a generalized distribution. And just in case that some of those functions is properly normalized so that it adapts to 1 when you sum up over the arguments, then I will denote it by bold letter. Okay, so that's just on the notation. Now I'm going to use it. Of course, we have a reason to use this notation. It allows us to extend some tricks from information theory outside of its usual domain. So it turns out they apply even if the objects that you apply it to are not normalized. All right, so now economics. So be there some set of individuals. So there is a discrete set of individuals, or finite set. All the sets are going to be finite in this talk. There is discrete time, and there is a virtual social planner who is going to redistribute wealth every period. So this social planner will enforce a stationary allocation of wealth, which is just a probability distribution. So it's bold actually, and it specifies how much of the share of the aggregate wealth Mr. I gets at the beginning of every period. So every evening, the social planner collects all the wealth, and then in the next morning, it gives the share of QI to Mr. I and then QJ to Mr. J, etc. Now this wealth evolves over the day. So each individual I will get her morning wealth multiplied by a gross return, which is just a function of I's identity. So these returns can be heterogeneous across people, because maybe Christoph has a higher return than I have. But it also depends on some shock. So there's going to be some random variable called omega, which is ID across periods, and it's drawn from some probability distribution. Now, here is where I'm going to use our notational norm, I'm going to rename. So this function, this return, would be normally and naturally called denoted by little r, but I'm actually going to denote it by q, and I'm going to pretend it's a conditional distribution. It's just a function of a shock and of a person's name, but I'm going to write it in this way, and together with this allocation distribution, those two objects are going to define my generalized joint distribution over i's and omegas. Let me give you a hint that this helps. So let me introduce the problem of the social planner. So our social planner will control the allocation. The returns in this talk are going to be fixed and exogenous functions, but the planner controls this allocation. He can choose it from some set of possible distributions, and her goal is to maximize the long-run growth rate of aggregate wealth. So let me explain what this formula means. If you are Mr. I, then on a day in which this shock was omega, Q of omega I is your return. This is the factor that multiplies your wealth. Q of I specifies how much you were given in the morning, or what was your share of aggregate wealth in the morning. So then this would be your wealth in the evening. Now, when I sum up across people, that gives me the aggregate wealth, or the aggregate growth rate, or factor by which the aggregate wealth was multiplied on a day in which the shock was omega. Now, every day has a different shock or a different realization of the shock. Logarithm turns this into the growth rate, and when I take an expectation, then I have a long-run growth rate of the aggregate wealth in this society. Christoph, you have a question?
Just a quick clarification question. So the omega is common to all people?
Yes, it is common, but this is without loss of generality because it can affect the functions q of i's in different way. So, Jonathan, you have a question?
Yes, I was just going to say, so is this allocation effectively like choosing a portfolio, or?
Yes, very much so. Well spotted. So I will reveal in the next example that a special case of this is the old problem of Kelly's betting. Thank you, Jonathan. Let me just give you a hint that our unusual notational norm is useful. So if you look at this, Qi multiplied by this pseudo conditional distribution is in our notation just a pseudo joint distribution. Now, if you sum up the joint distribution across i's, this is like marginalizing. So this is in our notation just q of omega. And so this formula has simplified a bit. Of course, we will do more tricks with this notation than this one, but it's a hint that maybe it's a natural notational norm. First example, that will be very much like Jonathan's remark. This example is going to be equivalent to Kelly's betting problem and will have its solution. So let's have a world in which every day, all of us but one of us will go bankrupt. And so the guy whose money survives is a random guy. And so omega in this example, drawn from some distribution, is just the guy whose money is not destroyed on a particular day, and that is coming from some distribution. So maybe Peter's money survives more often than mine. So then this return function would be just like a Kronecker delta function. So if omega is equal to Peter, then Peter's return is 1 and my return is 0. If the social planner is unconstrained, so that she can choose how much wealth every day to give Peter and how much wealth to give to me, then this is a very simple problem. And it turns out that the optimal allocation that maximizes the growth rate, or in this case, just minimizes the speed with which we lose our aggregate wealth, would be proportional betting. It would allocate to each of us the share that would be equal to the probability of one person's money to survive any given day. In particular, it would not be optimal to give all the money to Peter, even though Peter has the highest chance of surviving, because eventually Peter will go bankrupt on a day. And so sharing the money among us will be like a kind of a hedging. And that turns out to be optimal. And this problem turns out to be equivalent to a simpler version of Kelly's betting problem. And also the solution of it is known as Kelly's proportional betting. Our model is more general because we have some constraints on the allocation, and also we will make some new observations about the constraint solution. All right, so I'm one slide away from the main result, but I need to define an object. So the main result on the next slide will say that a gross optimal, gross maximizing allocation is in some sense most fair one. It's close to merits of each of the agents with respect to the gross. So for that, to formulate it precisely, I have to define what these merits are. So on this slide, I'm defining a merit distribution. Let me first do it for a specific period in which the shock realization was omega. And let me ask how much an individual I has produced, like what's the share of the aggregate wealth that this individual I is holding at the evening of this period with the shock realization omega. So this guy I got QI in the morning, then she got the return given by the shock, and this is her wealth at the end of this period, and the denominator, what I'm dividing with, is just the aggregate wealth. And so this would be then this share. And if you look at this, this is formally a definition of a conditional distribution, if these were true distributions. So I write it as a conditional distribution of I given omega. And then the merit distribution is just this object averaged across all omegas. So verbally, what it means is that I take a random period, I pick $1 at the evening of that random period from the aggregate wealth, and I ask, what's the probability that this dollar has been produced by Jonathan or Christoph or Peter or me? And these probabilities would be the merits. If most of the dollars are produced on a random period by Peter, then Peter would be called, in other words, to have a high merit in respect to contributing to the growth. All right, so here is the result. The result will feature what is called a Kullback-Leibler divergence. For our purposes, what we need now is that it's just some pseudo distance between two distributions. It takes us two arguments, two distributions, and it tells you how close these two distributions are. The result is a necessary condition on gross maximizing allocation, noted here by Q star. So that's the allocation that maximizes this growth rate of the social planner. And the result says that it's also the most fair allocation in the following sense. Take Q star and compute this merit distribution under that gross maximizing allocation. So this tells us how useful to gross Peter versus Christoph and Jonathan and me are. So I'm picking up on you because you're on my screen. I don't see the other names. So once you have this merit distribution, fix it and consider all possible other allocations, all possible deviations of the social planner. And out of the feasible ones that are possible for the social planner, choose the most fair one in that it's closest to the merit distribution in terms of Kullback-Leibler divergence. And it turns out that if you do that, it spits out the optimal distribution that you have started with. So that's a property of the gross maximizing allocation. It must be most fair in terms of being closest to the merit distribution. Alexandros, please.
Sorry, I think I missed that. But what is M? So how is the merit calculated from the model?
Yes, very good. So that was the previous slide. So the merit distribution is the probability that if I take $1 at the evening of the random day, that it is of Alexandros, that this is Alexandros dollar. That would be your merit. So merit distribution is a bunch of positive real numbers that add up to 1, and these are shares to something like a measure of productivity, but it also bundles together the allocation. So if you are getting a lot of money every morning, then also a lot of money are in your pocket in the evening.
Yeah, thanks. I just missed the notation. Sorry.
No problem. Thank you. All right. So that's the result. I'm gonna illustrate it. By the way, I should have spent some time clarifying what we mean by this constraint Q. So capital Q is a set of feasible allocations, and it may be pretty much any set. So maybe Alexandros is very respected, and so the social norms require that he gets at least 2/3 of aggregate wealth every morning. Or maybe the differences between our allocations cannot be too large. So any such constraint is fine, and the result holds for all such specifications of the feasible set. Here is another example. So just for the sake of simplicity, be there no uncertainty. So the set of states is a singleton, and be there 5 individuals. And I'm going to use the name of the individual to specify the individual's return. So Mr. 5 is very productive. Her money multiplies by a factor 5. Mr. 1 is not too productive. But there is so without constraints, you would give everything to Mr. 5 in terms of maximizing the growth rate. But there is going to be an inequality constraint in this example, which requires the entropy of the allocation to be large enough. This just means that the distribution has to be close enough to the uniform distribution. It turns out that an index which is used in applied literature called Thiel index can be interpreted in this way. So this just means that there is the allocation shouldn't be too unequal. So this turns out to be tractable, this example, but doesn't matter much. So what you would do is that you would give the largest share of wealth to Mr. 5 and the smallest share to Mr. 1, and it would be monotonic. You would give some share to everybody just because of the constraint. Jonathan, please.
Jonathan, you're muted.
Jonathan, you're muted.
Sorry, I was. So the QI is that's the effectively the expected return of investing in I.
No, QI is
QI conditional on the state.
Yes, this one.
The one, yes, it's like the
one.
expected return of investing in I. I mean, the thing at the bottom is the expectation over P naught.
This one.
Yes.
Yeah, so let's go over these objects. These are important. So QI is not a return because it does bundle it is also affected by the allocation itself. So QI conditional on omega is the answer to the following probabilistic question. Pick any date in which the shock realization was omega, wait till the evening, pick a random dollar from the aggregate wealth, and ask with what probability this was Mr. I. So it's a conditional distribution of the people owning a dollar, conditional on the shock realization. Now, this merit distribution is the average across that. So the only difference is we don't do it on a period in which the realization of the shock was omega, you do it on the random period.
Okay, sure, but it's like a return. And what I was going to ask is, jumping to the KL, I mean, what the KL does, you're taking an expectation over logs, right?
Over log ratio. I will show you later on. I will show you what the KL.
Okay. I'm just fine. I think I can see what's.
So it's not a return. So let me clarify why this merit distribution is not just a return. So it would be merit of Jonathan would be high, can be high for 2 reasons. Either Jonathan is a very productive guy, so whatever little money he got in the morning, he turned it into a lot of money, unlike the rest of us. Or maybe Jonathan isn't as productive guy, but we are living in the world where Jonathan is given a lot of allocation in the morning. So maybe Jonathan is as productive as us, but since he got 90% of wealth in the morning, well, he also has a high share of the wealth in the evening. So the merit is something which in our world combines both allocation and the returns. All right, so here is my optimal allocation. It gives most money to the most productive guy, but it's kind of smooth. And given that allocation, I can compute merits. So let me do that by a click. So the merits are the red dots, and this is going to be a bit more unequal distribution because Mr. 5 is not only very productive, but he's also getting a lot of money in the morning according to this optimal allocation. So in particular, this merit distribution is too unequal. There is no allocate. This is not a feasible. It's a distribution, so it's an allocation, but it's not a feasible allocation because it's too unequal, and the constraint was binding for the optimal allocation. But I can ask, given that merit distribution within the set of feasible allocation, that is those that are not too unequal, which one is the closest to the merit distribution in the sense of being the most fair? Well, that's the interpretation. And if I do that, I get this blue distribution, which happens to be the original growth optimizing allocation. So again, the original blue distribution wasn't computed based on some distributional fairness consideration. It was just a growth maximizing allocation. But given the merit it produces, it's also the most fair. That's the result. Let me clarify that the planner is not obsessed with the fairness. It's not the case that the planner would like to minimize the Kullback-Leibler wedge or difference between the allocation and the merit distributions. The planner could do that by changing the allocation, but that would decrease the growth rate, and the goal of our planner is to maximize the growth rate. And the reason for that is that this is why we call it a naive merit principle. When you are doing this optimization over the fairness or consistency, you are keeping the merit distribution fixed, computed under the growth maximizing allocation. Now that the merit distribution changes as you are changing the allocation. So if I give a lot of money to Peter, he will have high merit, but the maximization, the optimization here ignores that. Now, incidentally, there is a nice experimental paper by a guy called Peter Andre from Bonn, who kind of does this in a field experiment. He let people judge meritocratic contributions of their peers and to reward them. And Peter Andre, that's how I understood his talk, was a little bit upset by the fact that people's meritocratic principles are shallow, and he calls his paper Shallow Meritocracy, where he points out that people do not incorporate indirect effects in their merit judgment. So there might be a reason why you didn't work hard. And the outside observers judging those merits somehow do not take those other reasons into account. And it turns out that something like that shows up from the first principles in our work. Right, that's I'm done with economics. So the next section is going to be about proving the result and explaining why it may hold. And this will be information theory mostly.
Can I ask a quick question?
Please.
So you call this fair? So I guess one could debate this endlessly whether this is then fair or not, right?
Yes.
Okay.
It's a necessary condition for the growth maximizing strategy.
Yeah.
That's what
I mean,
it is. Yeah. Everything else is a language. Right?
Yeah. Okay.
No, but thank you. I mean, fair enough. All right. So the first slides on this technical part is boring. It's just pointing out that I'm extending the definition of KL divergence. So KL divergence, I think Jonathan has alluded to it, is given by this formula. It is defined usually for two distributions. So it's a map that takes two distributions and returns a positive real. We are going to allow for the second argument to be a generalized distribution. So it can be just a bunch of non-negative numbers. Doesn't have to be normalized. And we're going to define Kullback-Leibler divergence by the same formula. We just don't insist both arguments to be a distribution. When you do that, then the interpretation of this function survives. In particular, you can ask, fix a generalized distribution Q, and look for a proper distribution that is most consistent, the closest in this Kullback divergence sense to Q. And if Q was a distribution, a proper distribution, then the closest distribution to Q would be Q itself. If Q is a generalized distribution, the closest proper distribution to it is the normalized Q. So you take Q, you normalize it, and you get the closest distribution. So Kullback-Leibler divergence is still, even with this generalization extension, like a consistency measure. Using that, let me now give you a bit long characterization of the growth maximizing allocation. It's going to be an outcome of some optimization program, which is bigger than the original one. So originally we have just maximized the growth rate of this economy. Here instead, I maximize some consistency measure. This minus shouldn't be here. I maximize some consistency measure or minimize the wedge between two distributions, and the set of controls have changed. So I'm still controlling the allocation, but then I'm controlling something new, some joint distribution of individuals and states. And a large part of the proof would be actually of trying to figure out what this other control actually means. The objective is not to maximize the growth rate. In this auxiliary characterization, the objective is to find the allocation and some auxiliary joint distribution that are most consistent. This little q here is the generalized joint distribution induced by the allocation. If you take an allocation and you multiply it with those return functions, you get a joint or generalized joint distribution. So this is really trying to find a pair of joint distributions that are as close together as possible. And there are two constraints. One constraint is that the allocation must be feasible. And the other constraint is that this joint distribution that we don't understand yet what it means has to agree with the prior on the margin. Now, if you do this optimization, then two things happen. The optimal Q will be the growth maximizing allocation, and then there will be another part of the optimizer, the optimal P, that turns out to be the same as the merit distribution that I have defined. So once you marginalize this P star, then you get the merit distribution that I have defined based on some pseudo fairness considerations. Okay, so what this P will be, it will be something that we will call a path. This path will be a path of money. It will be something that describes how money moves around this economy. And it turns out that there will be different paths of money. So we'll be describing stochastically how money move around the economy. We will let those different ways of money moving around the economy compete against each other. So that's just a hint, and I will unpack this slowly. So now, to prove this previous proposition, but also to help with the interpretation of it, I'm gonna prove a technical lemma. So this is basically pretty much like that long monster on the previous slide. It's just gonna be shorter, it's on simple objects, and it's also useful in proving it. And I think I can convey you the proof of this simple thing. So let me explain what the lemma says. It says take any non-negative number function from the finite set. So now forget about my economic application. This is just a simple piece of math. So take a finite set, take any non-negative map to positive reals, and for some reason be interested in the logarithm of the sum of this function. So this is a logarithm of a sum, and now I claim I can express logarithm of a sum as an outcome of some consistency optimization. So I take this Q, I call it a generalized distribution. It's not normalized, but at least it's positive. And I look across all proper distributions. I'm trying to find the one which is closest to Q. And it turns out that that logarithm is just the outcome of this optimization. And then the question is why and what this distributions P over which I optimize here mean. Can I interpret this, and how does it relate to my problem of growth? So I'm going to prove this in 2 slides. All right. So the first step in the proof is that I'm going to set up a growth process. So I'm going to take this sum that I'm interested in. I'm going to keep multiplying it or powering it to t. That gives me a process yt. And then the expression of the interest, this logarithm of this sum, is just the growth rate of this process that I have just created. So now I have this process where I keep on multiplying this sum, and just using a second, the high school mathematics, I can just multiply. I can expand these multiplied brackets, and that gives me that yt for any horizon t is just a sum over all sequence realizations when I'm taking all these sequences x1 up to xt. And the summands are the products when I keep on multiplying alongside these sequences the values of this function q in each adjacent member of this sequence. So this is a high school math. If I have seen it for the first time, I would be a bit confused, but there is nothing really complicated here. You may notice that the details of this sequence do not matter. Like a permutation of the sequence wouldn't change the summand. So I can pull together all the sequences that have the same empirical frequencies of these elements, or the same empirical distribution, and they would give me a same value of the summand. So let me do that. Let me take an empirical distribution P, let me sum across all empirical distribution, and I just need to keep track on how many sequences are there with a given empirical distribution. And I need to be careful about that because this is going to vary a lot. So if the empirical distribution is deterministic, if it puts all the mass on one value, then there is just one such sequence. If the empirical distribution is uniform, like 50-50 for a coin flip, then there are many such sequences if the horizon is long. And the number of the sequences with a given empirical distribution grows exponentially with the length of the sequence with the rate equal to the entropy of that empirical sequence. That's a result from information theory. So now, equipped with that, my process YT is just the sum across all empirical sequences. Then this part is this multiplication alongside this sequence. I get the realization of x, px times t, and I keep multiplying this. And this is just the adjustment of the number of sequences with that empirical distribution. And then if you do a very simple algebra and recall the definition of Kullback-Leibler, then this is equal to this. So what happens is that I have expressed the process of my interest, YT, as a sum of exponential growths, where each empirical frequency has its own empirical growth, exponential growth, where the growth rate is given by the Kullback-Leibler between the empirical frequency and the target generalized distribution. Now, when you are summing up exponential functions, the good thing is that you can forget all but the one with the highest exponent, at least asymptotically, because the one with the highest exponent is going to outgrow all the others. So I don't have to sum up all of them. I can just take the one which has the highest exponent, and that's the one that minimizes the Kullback-Leibler. And that's the proof. I have found my process to have a growth rate which is given by this minimum or minus minimum, and I was interested in the growth rate of this process. My experience is that this deserves some unpacking, so I have some discussion of this proof. So let me give you an intuition. So okay, what was the result? The result was that the logarithm of a sum is an outcome of some optimization where I'm optimizing some consistency across all distributions P, and consistency is with respect to this target function Qx. Okay, so what are these distribution P's? Well, each P corresponds to an empirical distribution of a sequence. I'm summing up over long sequences. Now, this process that I've been discussing was the sum of growth processes with across all empirical distributions, but I could have just taken the one which grows most quickly, and that was the P that generates the growth process that dominates all the others. So now the next question is, why is it the case that the empirical distribution closest to the target function Q has won this race of growth rates? Well, if you wanted to do well, then you would choose a distribution that matches those values x that maximize this function Qx. I mean, ideally, you would put all the weight on the maximizer of Qx, because you're multiplying these Qx's. But that would be a mistake because that would be a deterministic sequence, and there is only one such sequence, whereas the distributions with uniform or close to uniform distributions, they have many sequences with that empirical distribution. So you want to do a compromise. You are looking for a sequence which puts a lot of weight on the values of x for which Qx is high, but it also should be as random as possible, as uniform as possible. It turns out that the optimal compromise is just to match Qx, is to match the function Q, but to be normalized because it must be a distribution. All right, this is gonna get better. Now I'm gonna take this lemma and I will go back to my actual object of interest. That was this indirect characterization of the growth maximizing policy or growth maximizing allocation. So with some understanding of the lemma, let me just tell you that if you recall the growth rate, the definition of the growth rate, it was this expression. You were taking the expectation over this state, so we're summing up the growth rate in each state, but the growth rate in each state was a logarithm of this, and this is a sum. And now I have a convenient formula for a logarithm of a sum. So the proof of the actual statement is just an application of the lemma. But let me do something more useful than just the algebraic proof. Let me give you an intuition, a verbal intuition for this result that explains the growth maximizing allocation as an outcome of a joint distribution where the adjacent control was just joint distribution over people and states, this pi of omega. So the intuition is going to give it an interpretation. So let me introduce the concept of the dynasties of dollars. So imagine the beginning of this process of growth. And at the beginning, this society was given a continuum of money, continuum of dollars. So keep track of every dollar from that continuum and think of it as a dollar, as a mother starting a dynasty. So I think here we are influenced by Arthur and his models with biological content. So this dollar is going to be a mother of a dynasty. And in each day, it's going to be in the hands of an individual. So this allocation distribution, sometimes give it to Christoph, sometimes to Peter, sometimes to me. And then on each day, there is going to be a shock omega that together with the identity of the owner, it determines the return that this dynasty is shocked by. So if it is a day in which I have a high return and this dynasty is in my hands, then it multiplies as many kids, it becomes bigger. Maybe it was a bad day for me or bad day for Peter. In that case, this dynasty shrinks. And this dynasty goes from Peter to me and then to Christoph, etc., randomly. And it also is hit by those random states randomly. And so I'm going to define the path pi of omega as an empirical frequency of this dynasty being in the hands of Mr. I and in the state omega. Now, in the long run, law of large numbers should implies that the empirical frequency of each dynasty enjoying the state omega is given by the prior distribution of those states. So they all are gonna have in long run the frequency of the states equal to the prior distribution. But some dynasties are gonna be lucky in that they will end up very often in the hands of Christoph, who happens to have often high returns. Or maybe they are in the hands of Christoph in those days where the state is such that Christoph has high returns. So some dynasties, as there is continuum of them, will be luckier than the others, and they will be in the hands of productive people or in the hands of people at days where they are productive. Now, of course, there is a cost to it. I mean, if you are lucky very often, then it doesn't happen to too many dynasties. But it turns out that the wealth of the dynasties with a path pi of omega grows at the rate exactly given by this Kullback-Leibler divergence between this path of the dynasty and the policy function given by the allocation combined with the returns. So this is something that I'm not proving you. This is something that you have to believe me. It's an outcome of some algebraic manipulation. But what I've got now is this formula. Now fix the allocation. So you are fixing this part. Now you are maximizing across all paths of money under the condition that on the margin they agreed with the prior state distribution. And you are asking which of those dynasties grows fastest. This minimizes the Kullback-Leibler. And then you allow for an optimization also across the policies, across the allocations, and altogether this joint distribution is the allocation that is determined by the planner, and then the competition of those dynasties of dollars determine the growth rate of the economy. So that's roughly the intuition for the result.
Could I ask a question?
Yes, please, Arthur. Hi.
I was just wondering if it would be possible to pension off the social planner. And I mean, what we have here is a story where there's something intrinsic about me that makes me a good person to give money to or a bad person to give money to. And okay, so which is different than the usual stock market interpretation, where it's just where it's the stocks that are good or bad, and the guy is reallocating money happily between stocks in every period. But it seems that there must be a way of getting rid of the social planner that replaces it with something like Arrow de Breur contracts, so that we have a bunch of money. Some of us did well, some of us did badly, but we have an interest in redistributing the cash across these people with different qualities in the way that you're describing. But
so let me pick up on this. So yeah. So I think I let me answer, and then we can have a follow up, and we'll see how I've got with understanding you. So first of all, both Jonathan and Arthur are right that if I call each individual an asset, then this is just a management of a portfolio. This is a hedging problem. And so if those I's were not called people but assets, then those would be assets that have random returns. And some asset has a higher returns very often, but sometimes does very miserably, or there is some correlation between assets and returns. And this is all fine with this model. Additionally to the standard Kelly's problem, we allow for constraints in allocation. So the standard Kelly problem says, look, there is a distribution, there is a set of assets, they have some stochastic returns, choose any allocation. Now it might be that maybe a pension fund cannot put everything on a specific risky asset, even though it would be optimal, gross optimal. So we allow for all kinds of administrative constraints in a portfolio management. And then we get a new property of this optimal asset allocation or optimal portfolio, which says, well, it minimizes some Kullbaum-Gleiber divergence, which I think was not known in this literature. So in the context of portfolio management, you indeed don't need a social planner. It's just a private investor who is managing his portfolio.
But I'm wondering whether you need him at all, even in your story. I mean, I'm not sure about the
in my story, you could say, well, there are different societies who have different allocational rules, and some of them are better than the others, and those who grow very quickly will be then very visible.
We want to take advantage of people who are like stocks in the regular model, so we do want to reallocate in order to get
right. Yes, and so the reason
why couldn't this reallocation arise with Arrow de Breur contracts? You give me some money, and I will repay you next period in some constant share way, whatever as my portfolio works itself out. And,
right.
and in that case, it seems that you wouldn't need to talk about fairness at all. This would just be a Pareto efficient.
Right. So
maximizing growth.
I will have a slide that will hint on how a society can get to the gross optimal allocation without a social planner. But indeed, we think of this social planner as just being an analogy to an evolutionary force. So if some societies are doing well in this respect, that they will be wealthy pretty quickly, or more quickly than the others. And now, if you are an outside observer and you tend to notice more wealthy societies more often, and that's all you will observe. But I will have a slide on an evolutionary interpretation of evolutionary implementation of the optimal strategy. So let me finish the proof of this meritocratic principle. So now, in particular, so I have translated this gross optimization, maximization to a joint optimization, but then I can just say, okay, fix the optimal path of money, call it P star, and just optimize the allocation, that is, find an allocation which minimizes this wedge, subject to the feasibility constraint. And if you do that, and I also should say that, and I'm going to skip the arguments for this. This optimal path actually happens to be agree with the merit distribution. If you do this optimization, there is a trick with Kullback-Leibler divergences. If you have a Kullback-Leibler divergences of two joint distributions, you can first compute the divergence of the marginal distributions and then put everything else on the side. So this is what I do here. This is called a chain rule for Kullback-Leibler divergences. And so there is some stuff that we don't need, and this is why it is in the gray. And this is the divergence of the marginal distributions. And if you just minimize this, then this is what is the meritocratic principle. So it follows pretty quickly once you buy our result that the gross maximization is a joint maximization of the path of money and the policies. Okay, let me go to Arthur's question. So here is going to be, and this is an evolutionary seminar, so it's appropriate. Here is an evolution or pseudo-evolutionary dynamics that leads to an optimal allocation. So start with arbitrary interior allocation, so at least everybody's getting a positive share, but possibly far from optimal. Compute the merits, that is, compute the how much each of us have contributed to the growth. So that combines that allocation and the productivities of us. Take those merits as given and update to the most fair allocation out of the feasible set. So there's going to be some Q prime. So given that merit, and iterate. So you've got a new allocation that changes the merit. So then find something fair again and iterate, and eventually this converges to the gross maximizing allocation. So a society that will buy into this fairness norm that Christoph said, well, this is arguable, but if the society would have this norm that it is fair to allocate as closely as possible to those merits, and they would chase this rabbit of fairness, they will eventually converge to the gross maximizing allocation. And this is something from convex geometry. All right, so that's the end of information theory part. And then I have a short part. How am I doing this time?
So you're 54 minutes in. Depending on how much time you want to leave for discussion, feel free to go through this or blitz through this, or as you want.
So maybe I will give it like 5 to 10 minutes at most. So let me tell you what the predictive coding is. So it's a bit amazing because it's so the most famous name in the literature is a guy called Friston, who has like 190,000 citations on Google Scholar. So he's one of the most cited scholars in the world. He talks about cognition, and I, who makes living in bounded rationality, didn't know about him until recently. So I think it either tells something about me or about the profession around me. So I'm going to tell you the model that these guys in cognitive science and machine learning are using as a model of brain. And it turns out that the society that we have studied is doing the same thing, that these things are mathematically equivalent. So a problem of predictive coding is a problem of a system, a biological or an artificial system, that is sampling a signal from some objective distribution. I'm going to use here a notation that is suggestive of the previous model, so all the notation shows you the links. But this is a different problem, at least on the verbal level. The system is not interested per se for the signal. So the signal is maybe some visual stimuli of your retina. Instead, you would like to form a belief about the cause of this signal. It's not really a cause in the terms of causal relationship. It's a correlate of the signal. Now, let's say for simplicity that you are given likelihoods of the signals given each cause. So you know this conditional distribution. These are encoded in your brain, and there's nothing to learn about these. But you don't know the prior distribution of the causes. You entertain some set of possible prior distribution, or maybe this set might just specify what your brains can implement. But there is a set of possible priors. Once you would pick the prior from the set, then you are good to go, because you would know the conditional distribution, the priors, you know the joint distribution, then you could do Bayesian updating. So you're going to choose the prior over the causes by this optimization, where this can be motivated, and this is how an economist would motivate it, as an outcome of asymptotic either Bayesian or maximum likelihood learning. So once you specify a prior that gives you a marginal distribution over these signals, and you are trying to look for a prior, this for a model of the world, that gives you the marginal distribution of the signals as close as possible to the true distribution. This is what would happen to a Bayesian or a maximum likelihood statistician if he would be collecting a lot of data. Now, this literature, the machine learning or the predictive coding literature, instead says that this guy wants to minimize, this system wants to minimize a surprise, so it's choosing the prior such that it minimizes this, where this is taken as a measure of surprise. So that's the problem. Once you choose your prior, then you can be Bayesian. You have a Bayesian model. Once you observe a signal, you could do a Bayesian update about the cause. So that's the problem. But then the cognitive folks tell us that this would not be tractable. This is not how the brain works. And actually, this is used in machine learning. This is not how machine works, because it's just not tractable numerically. So instead, they do something indirect. They say, let's have two models. One of them will be called a generative model, which is going to be a joint distribution of the causes and omegas. And that's this model here, when you are known these likelihoods and you are choosing a prior. So the prior together with those conditional distribution would be a generative model. But this is accompanied in the same system by a recognition model, which is a distinct joint distribution of the causes and signals. And this recognition model captures the system's interpretations of the signal. So this is how it works. Upon observing omega, you can form an arbitrary belief about I, that is a distribution, but you sample signals from the true distribution. This is given the P0 of omega. That's an objective distribution. So your recognition model has to have a marginal distribution that coincides with that. And then your recognition model is just that true marginal distribution multiplied by your beliefs. So since you can have arbitrary beliefs, there is no need for those two models to be somehow consistent. But it turns out that a good pair of these two distributions is as consistent as possible in the following sense. It turns out that the best fit, that's the prior that the Bayesian would arrive to, or the Bayesian statistician or the maximum likelihood statistician would arrive to, solve this joint optimization over the recognition system and the generative system. Subject to the recognition system coincide with the true distribution of the margin and the prior being feasible for yourself. And turns out that this problem is exactly our problem of growth. And so let me give you a connection. Why are these two problems equivalent? Well, because it's a problem, both of it is a problem of stochastic growth. So in the first part, the long part of the talk, I was maximizing aggregate wealth. What is it? It's a product of random returns of aggregate wealth. What is that? Well, you sum up across people, you take the allocation of a person and multiply it by the returns of those people. Well, these are not distributed probabilities, but some positive numbers. In the case of the statistics, you are maximizing the likelihood of a sample. What's it? What's that? Well, likelihood of a sample, you are observing signals omega t. What's the likelihood of each data point? Well, you sum up over all possible causes. These are latent hidden variables. Take these prior probabilities and multiply by this likelihood function. Now, those two things are ostentatively the same expressions. And so in both cases, you are just maximizing the growth rate. In one case, growth rate of wealth. In the other case, growth rate of the likelihood of a sample. But the mathematics doesn't really care. And so we get this translation. What we have called an allocation returns is called in this predictive coding literature a generative model. And in this case, these are truly joint distributions. Everything is normalized. and then what we called a path, and we interpreted that as a movement of money or path of money, is called a recognition model in this predictive coding literature. And so, I mean, these things are kind of the same. And for us, you know, we have been playing with the growth, and then we have realized that this is equivalent to something in statistics. So for us, it was also a way how to understand this predictive coding literature, which is written by non-economists, and they don't use the standard statistical language. So for us, it was difficult, and this growth perspective helped us to understand the predictive coding. There is even an analogy of this naive meritocratic principle. A good system, the biological system, it's trying to choose the distribution of the causes such that when it learns about those causes from observed signals using Bayesian updating, it gets a distribution of the causes which is as consistent as the predicted distribution of causes. So this predictive coding says, well, I have a prediction of the distribution of the causes. Then if I have it, then getting a feedback from observed signals, I learn another distribution of the causes. Now, since I misspecified, those two things will not be exactly matching each other, but I will choose a model that matches them as well as possible. And that turns out to be a model that a good statistician would choose. That's it. I'm done. So we have established an equivalence between economic growth and a statistical model. It has give us some consistency principles that has a meaning that we have related to meritocratic principles in economic contexts, and these are consistency principles in terms of cognition. The way they prove those indirect characterizations in the predictive coding literatures are different from our arguments. So we use proof based on growth, and we found that to give us some useful intuitions about why these results apply, whereas they use a variational approach, which we found we struggled to understand a bit. So we think that maybe this growth-based perspective might be an helpful entree into this literature for an economist.
All right, thank you very much, Jakub. I will stop the recording, and then we will have about 50 minutes to discuss.